In today's video we're doing some real life physics. Got two kettles, a new one made from stainless steel and a plastic one. The plastic one is rated at 1800 watts to 2200 watts. The newer stainless steel one is rated at 1500 to 1800 watts. We're going to put 500 ml of water in each, cold water, and we're going to see how long they take to boil and which of the kettles is most efficient. I've got them plugged into energy meters. I'll start the experiment and we'll talk a bit more about it. So switching them on together. So the stainless steel one is running at about 1700 watts. The plastic one is running at 2150 watts. I'm going to change them to the kilowatt hours setting so you can see how much energy they use. We've looked at the power rating. This one's a lower power kettle, this one's higher power. So 500 ml of water, half a litre, should take the same amount of energy to boil it. So the more powerful one should boil it quicker than the lower powered one. I've started a stopwatch as well. Started a few seconds after I boiled it, but it will give us a comparative time of how long they take to boil. Now, I believe our school bought these stainless steel kettles to replace the plastic ones because they are lower power and they thought they would be more efficient and take less energy to boil the water. I can see the plastic one, the water in there is boiling already. It's actually vibrating the bench. Just pop the lid and it's stopped heating, so that has boiled half a litre of water and taken 6.06 kilowatt hours. You might think the stainless steel one's lower power, it should boil it in the same amount of power, but it loses more heat through the sides and it's taken longer to boil, but it has used exactly the same amount of power. Now it'd be worth trying this with more volume, 1 litre, and see if there's any difference with a greater volume of liquid. With the kettle on longer, the stainless steel one might lose more heat through the sides of it, and there might be a difference if it is on for a longer period. So if we want to use our results to look at the specific heat capacity of water, the specific heat capacity is the amount of energy it takes to raise 1 kilogram of a substance by 1 degree. So the change in energy is equal to the mass times the specific heat capacity times the difference in temperature. So we had 0.06 kilowatt hours, which is 60 watt hours, and to get it into watt seconds, which is joules, we have to times by 60 to get it into minutes and by 60 to get it into seconds. and that equals the mass, which was 0.5 kilograms, times the specific heat capacity, times the temperature difference. Now that our water is quite cold, it was probably at 10 degrees, so the difference in temperature is 90. So this will give us 216,000 joules, and if we swap these around, we can divide it by 0.5 times 90. So our specific heat capacity works out at 4,800. The accepted value for water is 4,200, but there's some losses. We don't only have to heat the water with the kettle, we have to heat the kettle element and the kettle, its body itself, and it's going to start heating the surroundings as well. So there's losses to the atmosphere, and we've had to heat more than just the water. We've had to get the element of the kettle and the body of the kettle hot as well. So we're always going to end up with a higher value than the accepted value. To get a more accurate value, you could start with a kettle that's already hot, and you could insulate the kettle as well, and obviously take more accurate measurements of the temperature.